Contemporary cognitive research often treat dreams as isolated events, fragmented memory reactivations, or episodic replays disconnected from a broader computational system. The Brain Kinematics Model, combined with continuity theory, approaches the sleep-wake cycle as a single continuous organizational trajectory spanning both sleeping and waking states. To observe this trajectory in motion, we can examine a temporally linked pair of dreams flanking an anxiety-producing waking event. By analyzing a dream from the night before the event and another from the night after, we can map the brain's changing organizational state. This pre- and post-event sequence allows researchers to observe the brain actively regulating uncertainty across the sleep-wake barrier. The mind is mathematically calculating and adjusting its cognitive load as an uncertain future becomes a fixed cost. Subjective dream experiences are rarely viewed through a quantitative lens. Cognitive strain is typically represented by a single scalar value for emotional intensity, but the BKM suggests a more complex structure. The brain state is modeled by a vector equation, S of t: amplitude, dispersion, compression, residual strain, and regulatory gain. At t-1, amplitude and dispersion map uncertainty. Post-event at t1, compression, residual strain, and regulatory gain measure processing success. Homeostatic recovery involves the structural transformation of a highly dispersed state space into localized, manageable parameters. Consider the first dream in our sequence, recorded the night before a stressful waking event. The dreamer is on a familiar bus, but their normal, stable position in the middle is unavailable. They are displaced toward the rear boundary of the vehicle. The physical architecture of the dream bus is altered. It appears significantly shorter than usual, with fewer rows and restricted seating. A large notch further distorts the geometry of the available space. In BKM language, these physical constraints represent organizational ones. This topological bounding box shrinking around data nodes illustrates organizational compression. The cognitive system is modeling reduced state space against high demand. This is formalized by the capacity loading ratio. Lambda equals occupancy over capacity. As the ratio approaches 1, freedom for additional accommodation disappears. The brain is representing anticipatory anxiety through spatial geometry and capacity limits. This spatial compression reflects the computational burden of anticipation. Before an uncertain event, the brain cannot possess an outcome. It must instead maintain multiple branching predictions regarding what might happen. These branching prediction nodes projecting from the compressed box illustrate high-strain dispersion. The system is struggling to contain an expanding field of possibilities within a shrinking organizational capacity. Near the end of the dream, a conductor intervenes to prevent an extra passenger from sitting in an already full row. The conductor invokes a structural rule. The row is designed for only 2 people, and the excess load is excluded. This pre-event dream demonstrates an active boundary enforcement mechanism. The system is attempting to structure and contain anticipated strain through the successful regulation of capacity. The waking event at T0 represents a severe organizational perturbation. It is the turning region of the strain arc. The actual event forces the cognitive system to collapse its probability tree. Reality selects exactly one trajectory, instantly eliminating the countless alternative branches the brain was previously maintaining. The brain's computational task shifts almost immediately.
The problem is no longer what might happen. It is now what just occurred, and how do we evaluate its meaning. This waking pivot drastically reduces the dispersion of possibilities, but it initiates a requirement for complex post-event reorganization and evaluation. The post-event dream, recorded the following night, abandons spatial compression entirely. Instead of crowded seating and shortened buses, the environment is defined by relational distance and mutual suspicion. The system generates an authoritative figure, the 19th century ruler Nasser al-Din Shah, to represent the necessity for external evaluation and legitimacy. The dreamer initiates a minimal test input, a greeting. Instead of the anticipated rejection, the authority yields an unexpectedly warm response, which changes the relational state of the dream. This social interaction functions as a predictive processing test. The central node sends a ping vector to an external authority. The resulting positive feedback loop overrides the brain's initially negative prediction. The authority figure repeatedly hesitates, moving between leaving and returning several times,
before finally committing to sustained conversation. Here, the external node oscillates across a decision boundary. The dream system is sampling the state space repeatedly before locking into a stable, positive attractor. A complex sequence follows regarding the publication of a book. A claim is made, verification fails, a discrepancy is identified, and a clarification is offered, eventually leading to full support. This multi-step logic is known as strain decomposition. The brain is taking a large diffuse anxiety and breaking it into smaller sequential regulatory loops that the system can resolve one by one. Post-event processing uses an expanding relational topology to verify uncertainty. The brain is no longer compressing space, it is negotiating meaning. Despite the offer of full support and war handshakes at the end of the dream, the dreamer remains skeptical of the Shah's underlying motivations. This lingering suspicion is not a failure of homeostatic regulation. It is a feature of a stable and adaptive cognitive architecture. Positive emotional resolution does not erase higher-level evaluative processing. Reality testing remains active even after the primary tension of the event has been resolved. The arc has transformed from the rigid geometric compression of the best dream into a final, highly specific state of uncertainty concerning motivation. A stable cognitive state successfully accommodates both support and skepticism. Adaptive homeostasis prioritizes the management of stress rather than its complete elimination. The complete organizational trajectory of the strain arc is now visible: compression, followed by encounter, followed by reorganization. Tracking the mathematical strain vector across the timeline reveals the mechanics of recovery. While dispersion and compression decrease, residual strain remains as a small, non-zero value. The system transitions from S diffuse, an unmanageable scattered load, into S bounded. This clearly defined geometric node represents the final homeostatic outcome. This sequence provides a testable framework for longitudinal dream research. By mapping these organizational variables over time, we can track the kinematics of stress across an individual's dream record. Viewing dreams as dynamic computational datasets provides a means to track the active kinematics of the brain. Cognitive homeostasis is the vital, active transformation of chaotic possibilities into a bounded, navigable reality.